Hello, this is Hyunjun Jung. Here we present our work HouseCat6D, a large-scale multi-modal category level 60 object perception dataset with household objects in realistic scenarios. Category level 60 pose estimation problems start with training multiple object instances in the selected categories and generalize on unseen object instances in the trained categories. The task itself is much more practical than traditional instance pose estimation problem, but there exists only one real-world dataset that covers categories in household objects, which covers only 3 instances per categories, as well as a smaller number of training scenes with checkerboard visible in all scenes, which makes the dataset less realistic. To provide better dataset for the community, we present HouseCat6D dataset, which features diverse 41 scenes that has 160,000 training posts with 10 million grasping points annotations on 194 objects in 10 household categories, including photometrically challenging ones, and has extensive viewpoint coverage and contains 3 modalities and, most importantly, annotation quality comparable to using robotic annotation method. To achieve this, we use infrared-based external tracking camera together with pointing device and camera rig that have infrared tracking body attached so that we can get the pose whenever the infrared body is seen from the tracking camera. The camera rig is composed of interval scenes depth 4-5 depth sensor together with lucid RGB camera with polarimetric filter to obtain polarimetric image with the depths. We designed a specialized pipeline that goes object scanning, tip calibration, pose estimation, trajectory recording, and refinement. For scanning, we use turntable 3D scanner to scan household objects in good quality. As mentioned, we obtained 194 high-quality meshes from 10 household categories. Once scanning is done, we calibrate the pointing device by pivoting on the one spot while capturing the pose of the body around 10 to 15 times. With this, we can obtain the tip calibration, which is a transformation between infrared body and the pointer tip. Once we have the tip calibration, we set up the scene and annotate the objects by measuring the surface of the object with the pointer tip for around 25 points. From the collected points, around 5 points are used for correspondence-based initial pose calculation by manually selecting corresponding points in the object mesh. And then I-speech follow with all the measured points with the point from the object for a refinement. By doing this, object pose to the world coordinate can be annotated. Once the object annotation is done, we perform the hand-eye calibration, that is calibration to obtain the pose between infrared marker body and the camera image sensor. When the hand-eye calibration is done, we finally record the sequence around the object. Here with the annotated object pose and camera body pose combined with the hand-eye calibration, we can get the 60 pose of the object, that is the object pose relative to the camera image center. However, obtained object pose can be noisy due to the line of sight problem of the tracking camera as well as synchronization issue with the camera's sudden motion, which can be characterized by the big offset of the rendered object mask on the image. To solve the problem, we refine the trajectory by inspecting object mask on all frames, and then fix the camera pose of the accurate samples and run call map. This way, the camera trajectory can be refined while keeping the scale unchanged. After refinement, we can see that rendered object mask fits much better to the image. With this pipeline, we obtain very reliable pose annotation regardless of the camera motion. And from there, we further obtained large number of grasping annotation. We show that our annotation quality is comparable to the robotic annotation method. With our dataset, we run pose estimation benchmark on 4 state-of-the-art category-level pose estimation method and ablation study on the best performing method with reduced number of the dataset just to show the impact of the large-scale data on the performance of the networks. We also train the grasping networks and show the robotic grasping experiment in the real life using the robotic arm to show that our grasping annotation is valid. Thank you for watching our video. If you have any questions, feel free to contact us with email or visit us in the poster session on Friday.